a sadder emoji than that. Well, that's the one. Oh my god, we're back. Alright, cool. Great. Um, I'm sorry about that. Yeah, it's not happened before. I don't know what was going on there, but yeah, we lost connection, so I moved location and changed internet. Um, Worst possible timing. That was mid this session, obviously, and also mid interview for Haroon doing a video interview for Y Combinator. So, yeah, like, please, guys, if there's any questions, if anything's not clear, if that autograd is not clear, if it's not clear what that is, if it's not clear what a neural network is, an activation function, or anything, you just got to put it in the chat here, and I'll read it. Okay, and try and check back here periodically. Cool. So back to where we were though. What was happening? Right. So we had we'd made our x and y the right shape. We were successfully passing that through the model, and we just wanted to plot it now. So so yeah, we just explained what autograd was, and that was because we tried to do this. We tried to turn our torch tensor into a NumPy array by using the .numpy method, but it said, as it should say now when we run it, you can't call NumPy on a PyTorch variable that requires grad, because it's part of that graph that I showed you in the last slide. And so basically what that means is that attached to well, basically when you manipulate that variable, whatever is happening to it, it needs to be able to be stored, with the gradient. It needs to be able to keep somewhere for the gradient, so that it can monitor how that variable changed in the graph, and hence basically keep track of the contributions from that variable to the loss and relating any weights to the loss, so that when we figure out how the weights need to change to reduce the loss, we're not losing any information because, say, we've converted it to a NumPy array and done some manipulation that PyTorch hasn't been tracking. Okay, cool. So it tells us what to do. We need to detach that variable first. So we need to basically remove it from the graph. So what is I think there's a good explanation of what detach does as well on this page. So to stop a tensor from tracking history, you can call the .detach to detach from the computation history and to prevent computation from being tracked. So so yeah, we're just going to get that prediction, detach it, and then call NumPy on that detached variable, and then we should be able to plot it. Okay, so this is our first instantiated model, and it sucks. Okay, so now we're going to try and improve it. And the way we're going to do that is by using the criterion to evaluate the performance, so to measure how bad it is using the mean squared error loss. And then after we've done that, compute the, we're basically going to optimize the loss, try and find the minima, which is going to take advantage of using a gradient-based optimizer, stochastic gradient descent, using the gradients of the parameters of the neural network to update those weights in the right direction. Okay. If there's any questions about stochastic gradient descent, how that works, or mean squared error loss term, please put it in the chat. If there's any issues with the chat, like email us, and we'll fix it ASAP. If there's any features that you want, which will be more useful than just the chat, then also email us, please. Like, get involved and let us know what we can do to make this more useful for you. I assume that you're all here because you wanna learn this and you're interested in doing so. So if this isn't perfect for you, let us know, and then that's exactly how we're going to change it. Right? Nobody's let us know so far. So if you do, it will. The way that we run this will be exactly tailored to what you want. So please do it, okay, for your own benefit. So we can make predictions and we can plot them and then we can show the plot. Now we basically want to run this in a training loop with where during that training loop we're making those predictions and then updating the plot. So everything above here is basically all just set up, and then we'll plot the data which we want to model on the on a plot, and then we'll do plt.ion, so turn on interactive mode, and then we will say, okay, the number of epochs that we're going to use, let's say 10 just to start with. Epochs is the number of times we're going to go through the whole data set, so we'll say for epoch in range epochs. So for every different epoch, what we're going to do, we are going to make a prediction. We don't want to print that. We're going to make a prediction. We're going to plot the prediction just to update what our function looks like. Then we're going to compute the loss. So we'll say loss is equal to, now we can use our criterion. We can call our criterion. So calling this MSE loss function, that sets it up and it returns us an object which we assign to criterion, and that criterion is callable, which means it has some function defined such that when we put call it by giving it these parentheses with some arguments, namely the prediction and the labels which it should be matching, i.e. y, then it knows how to compute the criterion. Okay, it knows how to compute the loss, and obviously what it's doing is computing the mean squared error, i.e. difference between those two things, and then returning that to us. Okay, is that clear? Cool. Right. Okay. Well, for now, keep going. So now we've got the loss. Now what we can do is we can use the immense power of PyTorch to get the derivatives for every different thing. Sorry guys, for every different parameter which is in our model which we want to optimize for, right? So we can do loss. Now we know how the loss was computed, right? So in the loss we have this grad function, and what we're going to do is we're going to do loss dot backward. So it's all good, yeah. I'm on Holly's Wi-Fi now. So when we call this loss dot backward, what's happening is that we're looking at all the gradient functions for how. Well, firstly we look at the grad function for the loss, for how it was computed, and then we'll look at the variables which contributed to creating it, and given this function which PyTorch has built in, we will update the gradient of those variables. So we have So let me just explain what that is again a bit more. So again, we'll just break that for the top, there, and then we'll say z is equal to, like I did before, torch.sine of x, and then we'll print x.grad. So that should work, right? Cool. So at the moment, the grad is none, right? So there's no gradient stored in the x variable. But then if we do z dot backward, what that's going to do is it's going to find all the gradients, find all the variables which contributed to creating that z. So yeah, when we call this backward, it's going to find the variables which contributed to making that z, i.e. x in this line here. And then in those variables, it's going to differentiate this z with respect to each of them. So now if we print x.grad, which remember was none before, if we run this now, what we'll get is there. Look at that. Wait, no, sorry. Grad can only be implicitly created for scalar outputs. Yes, so z is a matrix. So actually, so let's just do like torch.sum to make it into a scalar value. I mean, this just, don't really worry about this, but just because you can't implicitly calculate the gradients with respect to a parameter for any non-scalar value. So before that was a vector, now I've just summed all of the values in that vector up, so it's a single scalar, so that we know that we're just calculating the rate of change of that number with respect to every other parameter. Otherwise, I think it could be ambiguous to which element of the vector which you want to calculate the rate of change of with respect to all the parameters that created it. Again, that's in this document here. So please check that out. And then let's continue. So we know now that every variable which contributed to the thing which we did backward for now has a grad attribute, right? So in x, we don't just have x, we don't just have the data, we have a grad, and that's what this is here. And so that has just been computed automatically using AutoGrad, and we can use that to update the weights by passing it to the optimizer. So remember when we set up the optimizer, we passed it all of the parameters which contribute to the loss. 1 second. Yo, Holly. Yo, the food is here. Probably. Alright. Alright, delivery break. Okay, cool. So, so we know the optimizer knows what it needs to use, which gradients it needs to use to do the update, right? Because we told it which ones it needs to. This is basically what parameters are you trying to optimize, and so hence what variables do you need to keep the gradients of, so that you can update them using some gradient-based optimizer like SGD. If anything I said isn't clear, please put it in the chat. Otherwise, I'll assume that this is going well. If this is like too fast or anything, then honestly, like, you gotta let us know. Otherwise, it's not going to change. But if you do let us know, it will change, because nobody else has asked for any feedback yet, and we really want to take it on board. Okay, cool. So, yeah, all right. Now we're going. And now, yeah, so we've done loss stop backward, and in all of the parameters which we want to optimize, we've put a grad, we've got a gradient variable. So now we can do the optimization. So we can do optimizer dot step. All right, now, okay, cool. So we're gonna step in the optimizer, and yo, shut up. All right. Okay. So we've now put in. we've got the gradients for each of the variables, which for each of the parameters of the model which we want to optimize. We've used them to take an optimization step, but there is a caveat, because when we compute the gradients using dot backward, what it does is it doesn't overwrite the gradients for each tensor. It doesn't overwrite the grad property for each tensor. It just adds to it, so they accumulate. So if we don't zero this and we keep running this optimization, what will happen is that the gradient in each of the tensors will just be added to, and hence it won't be equal to the latest update. It won't be equal to the value it should be, which is the slope of the loss at that particular parameterization. It will be the sum of the slopes of all of the previous parameterizations. So what we need to do is do optimizer dot 0 underscore grad, and this sets all of these parameters which we passed the optimizer, all of their gradients to 0. So now the model has changed. Now we'll go back to the start, and then we'll run it again. We'll just keep going through this loop for 10 epochs, which is just 10 tries, which isn't very much, so I'll put 100 actually. And then at the end we'll just print epoch, we'll print what epoch we're on, print the batch, no, we won't print the batch, sorry, we're not doing that right here, and then we'll print the loss. And then we'll do loss. Because loss is a scalar, so actually, hang on, let's just, yeah, so loss is a tensor, okay, so it's going to say tensor, it's going to have a bracket, and then it's going to have some number. It's just a scalar, so there's only one number, and it's going to have an end bracket. So we don't really want to, in this line, we don't want to print tensor, bracket, number, close bracket, dtype equals torch.float64. So because it's a scalar, we can do loss.item. And because it's a scalar, it has that attribute, and that means we can just get the numerical value from it. Let's run it. Okay. Hang on. Okay, cool. So that didn't work. Where didn't it work? Inline 49 in module. Loss is criterion of prediction. And why? Yeah, this NumPy array has no attribute. Requires grad. So what we need to do is use the capital Y like that, and there we go. So you can see the loss was decreasing over time. It ran so quickly we didn't even get to see the graph though. Looks like it's slowing down over here. So let's just do plt.pause. And I just realized we haven't updated the plot here either, so we're going to need to change a few things. So firstly, we're going to create a, rather than just do everything manually, automatically with PLT, we'll do figure. So we'll create a figure, and this is so that we can get a hypothesis axis. So just some axis for us to show our model, our hypothesis on. That'll be on that figure. We'll add a subplot. If you want to look at these, you can just check out the matplotlib documentation as well. Takes so 1 1 1. We'll have one row, one column, and this will be the first plot. And then we will do not plt.plot, but hax.plot, and then turn on interactive mode, show that, and then we'll do h-axis, hypothesis axis plot. And then if we run this, oh no, sorry, wait, firstly we just need to update it. So we need to do fig.canvas.draw. So that just on the figure, it gets the canvas, which is the editable part of the figure, and then it draws, i.e. updates the new plot. So let's run it and see what happens. Cool, alright. It exploded. Now, just going to change a few things. So we'll plot, we'll always plot in the same color. We'll plot in green. You can do color equals green if you want. and we don't want to plot all of the hypotheses at the same time. So after we create one, we want to remove it. So we'll just say like we'll just create some dummy variable. No, actually we'll give it a name so it's meaningful. We'll be like line is equal to that, and then after we go around to the next iteration, we'll do line. So line is this plots on the axis, but it also returns us something. It returns us a collection of the lines which we've plotted on the axis. So from that collection, which is a list, we just want to get the first one and then remove it. And so that's how you do that. So there you go. You can see our function learning something. Okay, but why is it not doing a very good job? Any suggestions? Any suggestions on what we've done so far? Points if you give a suggestion. Thank you for staying late as well. I'm sorry about that delay. God, this is awful. Please just like, if the streaming is okay, just somebody write yes here, please. Like, if the streaming is alright, if it's like really consistently breaking or anything, just tell me. But otherwise, like, if someone could just write yes there, that'd be really appreciated. And just let me know. Okay. So, now, why was this happening? Well, also, yeah, if you got any suggestions of why, then please put it in there. It could be the learning rate, okay? So we could try changing the learning rate, see what happens. Perhaps it's going too fast, optimizing too quickly. Well, that's already looking better, actually. That was a better improvement than I expected to get from that. That's not bad, even. Okay. But the real problem is that even though we've called our optimizer stochastic gradient descent, what we're doing is not stochastic gradient descent. What we're doing is gradient descent. There is no stochasticity in the loss function because we're always using the same examples when we make a prediction. So always the function, as long as the regardless of how the parameters change, we're always using the same inputs. We're always using all of the inputs, and all of those inputs contribute to they are, the output of the model is a function of those inputs. So if the inputs change, then we'll be optimizing a slightly different function every time. And if we pass in all of the data points at once, this gives us two problems. One is that for every forward pass, we need to compute an output value for every single one of those inputs. If we have a huge data set, that's going to take us way too long, and all of that would just be for one optimization step. The second thing is that when we the second thing is that when we are taking that optimization step, which is based on all of the examples, we're optimizing for them all at the same time. And it's kind of a case, what it shows, it's kind of a case that, optimizing for all of them really optimizes for none of them particularly. So instead, what we do with stochastic gradient descent, we split the data set into small mini batches, and then we'll do a forward pass for each mini batch, and then we'll do an update based on that. So I realize we're way over time, so if you want to go, like, that's fine. If you want to hang around, I'm going to implement a custom data set to show you how to create mini batches and like do much better optimization. So we'll start back up here. We will we'll import from torch.utils.data. We'll import dataset firstly. Okay. We'll also import data loader, just so I don't have to go back up. So we'll say that we'll create a class which is a my dataset, and that's going to inherit from that dataset object from torch.utils.data. Okay. Now we're going to initialize it so that when we create a dataset, we pass in basically the features and the labels, which are our x and y. That's what we're going to pass in here when we create it. Then we'll say self.features. So the features of this dataset are equal to features, and we'll say that the labels of this dataset are equal to the labels. And then we'll say, so now we need to define two things. So this class here requires us to define two functions. One of them is the getItem function. GetItem function. Now note, so just like in it, right? These have these double underscores either side, which means they're magic functions. And so this means they're called not when you call the object dot double underscore init or double underscore getItem, but when you do something particular. For example, init is called when you initialize the class. When you make a new instance of this class, then this is called implicitly. GetItem is called when you try and index it with square brackets. So so when we create the dataset, we'll say something like my dataset. That takes in the features and the labels, which are x and y. Then we want to be able to be like, okay, cool, I want to get a dataset item 10 or 11 in that case because it's 0 indexed. We want to be able to do that, right? But this thing, this isn't a list. It's not a list, and it's not a dictionary. So we're not going to, that's not going to make sense unless we tell it how to do so. And the way we tell it how to do so is with this getItem. GetItem defines what to do when you index an object of this class with some number. Yes, we're just wrapping up, just getting it too involved with this. All right. Feel free to eat without me if you want.
It's fine.
So getItem, right? It defines what to do when we do indexing. So we'll say that the x is equal to self.features of so getItem takes in what index you want to give in the square bracket indexing there. So we will get the index. So we'll get the features at that index, and then we'll get the labels at that index as well, and then we'll return them. So we'll return x and y, and then we'll print this just to show you what it looks like. Run that. Cool. So here is what that returned us. That was that last print, okay, before we encountered the error that I put in there. So yeah, we just got a single scalar value back for x and a single scalar back for y, okay? And yeah, so now we've returned those two items. Now what we're going to do is we're going to create something called a data loader. So we'll go to the data loader section. Now we're going to make another class. No, we're not going to make a class. We're going to make a data loader. We're going to make a data loader, and that's going to be called, that's going to be an instance of the class data loader, which takes in a data set, and then you can tell it what batch size you want. So let's say like 4, and then we can also tell it, do we want to shuffle the data set as well? True. Okay, cool. So this data loader, what it does is it uses the data set to get items like we did there, and then it collates them together in batches, in this case of size 4. So so just to show you what that looks like, So oh, okay, cool. Yeah. So I said we need to implement two functions for this data set. They're not including the init. So another one is the length. Another magic function. Double underscore len. And so this defines well, what do I return when somebody asks me for the length of the data set? So I'm going to return the length of, say, the features, which should be the same as the labels. You can see here, print length dataset. Now that will now it knows what to do. Okay, because before, like, this dataset was just a class. It was just an object of this class. Well, what do I do if someone asks me what my length is? I don't know. Like, I don't know what I'm supposed to do. I'm not a list or a string or a dictionary or anything, so I don't have length implemented. Well, now you do. Now it knows what to do when I ask it for its length. So that will return us, see that 30? Yep, because I said m equals 30 at the top. So that's all good. Now we can make a data loader from it, and we'll just print the first item in the data loader. So there you go. Now look, the data loader, so we can basically iterate through the data loader here. That's what I've done there. So I've just printed the first thing that's in the data loader, and then I've broken out of it. First thing in the data loader is this basically a tuple of two things. First one is the features, second is the labels. And that's the Y and the X for those four inputs which the data loader has collated together. Okay? So now okay. Now we can pass those small batches to our model, right? So we'll say here for batch in data loader then we'll get the features and the labels equal to the batch. So that batch is, it's got two things in. The first is the features, the second is the labels. And then we'll go forward, we'll pass the features forward through the model, and then we'll plot those predictions against X, okay? Now we can't plot X against Y now, because we can't plot X against Y anymore. Sorry, the X against the prediction now, because, well, that X, that's all the examples, and this prediction is only 4. So let's just leave that for now. You saw the function optimizing earlier. I promise that you look better, and I'll release how it looks when it really optimizes using this stochastic method later. But for now, let's do that and see what happens. Okay. Cool. Well, there you go. You can see how okay, yeah, the loss is going down, but you see how it's jumping all over the place, right? Well, that's because we're randomly sampling from that data set at all different points, and getting back and yeah, like having a different loss surface every time. That's not the loss surface. That's the model. So yeah, that's how you train and build a neural network. Is that better or worse? I think one thing we can remove is this. Okay, cool. I don't know if that's quite optimizing right now. To be honest, I'm gonna go eat right now, and then I'm gonna tune back in later. If you want to tune back in later, meet me here at 11:30. All right. Otherwise, I'll just release the code and the video on the Hacker Hustle YouTube and website. So if anyone's still here, you are amazing, cool. Yo, yeah, let me know who you are, because I like you guys. I like having you. You're dedicated. I want to know who the super fans are and build a product for you. Okay, what is it you want? Enter your email here, and tell me. Okay, I'll give you a challenge. I'll give you 5 hacker points here if you each give me an improvement to be made. Okay, and I'm going to release in the next few days what it means to get hacker points and what you can get for it. So please, let me know at least one thing which we could improve here. Is it too fast? Is it too slow? Is it too much theory? Is it too much code? Is the code not big enough? I don't know. Are you full screening this? Like, let me know how you're using it as well. Yeah, are you full screening this? Do you like using the chat? Would you rather send photos? Would you rather like be on a video call with me? With this many users, like, it's doable. So please let me know. All right. I'm gonna eat. Hacker Hustle, day 5. Thanks for being here. Shout out to Charlene. Peace out for now. Tune in at 11:30.